was this u hat, which is a function of t, and it's e to the minus I over h bar, and then h hat t, where h hat was is the Hamiltonian of the system. And the expectation value of h in any particular wave function or state is the energy, is the average value of the energy. So if I have a collection of particles, each in the state psi, and I measure their energy, I will get, that's given by the expectation value of the operator h. So now if we have another operator that is not necessarily time dependent, so let's the time dependence of some observable that is itself not time dependent. So in this case, I mean that a of t is not a function of the time explicitly. Okay, but nonetheless, we can ask what's this question, what's the time evolution of this observable A in some state? If the state is evolving in time, so if the state evolves itself into time, according to psi of t is equal to this u, the time evolution operator of t times psi at t0, for example. So when we when we take the expectation value, psi of t, and we have a, the operator psi of t, in here, this will be time dependent. Okay? So that makes sense. I mean, if the state itself is changing with time, then the observable, if I take the expectation value in that particular state test, I should get something that's time dependent. Okay, so we can write this. So let's write the state psi of t in terms of the time evolution operator. So let's write psi of t a hat, psi of t, just write it as psi at time 0, and then we'll write u hat dagger, because I have to flip it around. Remember, when I take it, turn it into a bra, times a, and then u hat, and then psi of 0, where the u hat, these are functions of t. So what we can do is we can call, let's define the Heisenberg and Schrödinger operators as the following. So I'll write A with an H in the upper little superscript here is equal to U hat dagger of T, A Schrödinger U hat of T. Okay, so we'll define, this is the Heisenberg operator, and A hat Schrödinger is just A hat, no time dependence. Okay. So now you can divide basically the way that you look at quantum mechanics into two pictures. So there are two major we call them pictures in quantum mechanics. And one is called the Heisenberg picture. And the other one is called the Schrödinger picture. And in the Schrödinger picture, we've already seen, we looked at what the time evolution operator does. If we inch forward, infinitesimally in time, we looked at what happens to a state kit. And we found that we had a differential equation, which was, we found that we had I h bar partial with respect to time of psi of t equals h hat psi of t. We have the Schrödinger equation. Okay, so in the Schrödinger equation, obviously, the state ket is a function of time. And in the Schrödinger picture, we solve for the state ket as a function of time. Okay, that's sort of one of the pictures. And the other picture is the Heisenberg picture, where the state kets are stationary, they don't change. The state kets are, I should say, time independent. And the operators have time dependence. Okay, and that time dependence we'll calculate here in just a second, but this is the relationship that we will explore here for that. So we'll find the time, we find the equation of motion of the operators. Okay, and so it's divided in each of these pictures. Some problems, are easier to solve in one picture or the other, and so that's typically why it's called the Schrödinger picture and and the Heisenberg picture. Sometimes you would want to use the Heisenberg picture, and sometimes you would want to use the Schrödinger picture. Although we won't get into problems that are so hard that it really makes much of a difference here, but when you start to get to real practical problems, sometimes it's much easier to use one picture or the other. Okay, are there any questions so far before we just calculate this operator equation in motion? Okay, so let's calculate, let's use this equation. So call this star. So let's use star to find an operator equation of motion. So we want to take, let's take the time derivative of a hat h. Okay, so that means we can just use the product rule, so we'll have d by dt of u hat dagger of t times a hat, and well, let's go ahead and leave the Schrödinger there, and times u hat t, and then we'll have plus u hat dagger d by dt a hat s, which is 0, and then u hat plus u hat dagger of t a hat Schrödinger, and then d by dt of u hat of t. Okay, so I just use the product rule. And if we've stipulated here that there's no time dependence explicitly in a sub s, so that would be 0. Now, so what do we have for the time derivatives of u? Well, u dagger, so u dagger, I just have a plus, I'll have a plus I here, so I'll have a plus I over h bar. This would be an I over h bar, h hat, times u, it's an exponential, so I'll get times u dagger, times a hat Schrödinger times u hat, and then on this term is 0, the next term will be u hat dagger, a hat Schrödinger, and now I'll have minus I over h bar h hat times u hat. Okay, so we can bring out an I over h bar, and then let's remember that as long as there's only an h hat in the exponential here, so that it will commute with h itself. U dagger and u will commute with h. So here I have I over h bar, and then I have h times u hat, or sorry, yeah, u hat dagger as u hat. So this is just h hat times what? This is just a hat Heisenberg. And then here I can take this h bar, or sorry, I can take this h and move it past the u here, so that I'll again be able to group u hat dagger as u hat. And there's a minus sign here, so I can write this as minus a hat h times the Hamiltonian again. Okay. But what's this? Right, this is just the commutator of h with a hat Heisenberg. And so we have the operator equation of motion, d by dt of a hat h is equal to I over H bar, H hat, A hat times M. Okay, so that's the equation of motion of A hat, and if there were, so this is what we just derived. If there were explicit time dependence, you would have plus d by dt A hat H. Well, it would be inside the inside. It would be, this term would be non-zero. U hat dagger d A hat S. If there were time dependence. Okay. So what does this equation remind you of? Have you seen it anywhere before?
Kind of reminds me of like the kinematic stuff we did in mechanics, but
How so?
well, like if you have I just remember there being differentials in it. Like I'm not seeing the pattern right now.
How many formulations of classical mechanics do you know?
Well, I know the force
Well,
equals.
I used to know more.
There's
And then I took the
Lagrangian,
exam.
Huh?
The Lagrangian.
Yeah, Lagrangian.
The Newton, Newtonian, and.
Euler.
Well, the Hamiltonian, I guess, is the other one.
It's three. There's one more.
Lagrangian, Hamiltonian. Wasn't there an Euler equation of motion too?
Probably
Or am I tripping?
Yeah, there's an Euler-Lagrange equation.
That's right, that's right. Euler motion.
Anybody know the fourth?
Newton.
Well, we already went over that one. There's, Newton, Lagrange, Hamilton, who else? Who's the other big name?
Einstein.
And just classical mechanics.
All right, let's start naming them all. Kepler.
Classical mechanics.
Copernicus.
Yeah.
Kepler.
I think Galileo had, pre-Newtonian.
Oh wait, is it tip of my tongue? I know this.
French guy.
That does not narrow it down.
Huh?
That does not narrow it down.
Poisson?
Oh, Poisson.
Yeah, I wasn't gonna get that one.
Oh man.
I was thinking somebody else.
Okay, so
Seem to remember that from linear algebra.
That is the one that I don't remember.
Yeah.
you might not have learned it at all.
Okay, I haven't seen Poisson since Chaos actually.
Poisson formulated classical mechanics in what are called Poisson brackets. And Poisson brackets that's the way that you go from classical mechanics to quantum mechanics. The way it was done originally by Dirac was to follow the Poisson formulation of classical mechanics, and just you turn the Poisson bracket into a commutator. So in the Poisson formulation of classical mechanics, if I take anything that I take a bracket with the Hamiltonian, that gives you the time derivative of the object. And so this equation here that we just derived is in fact just, if you turn these square brackets into curly brackets, you have the Poisson, the Poisson bracket. And that's the most important formulation of, well, the Hamiltonian, and, well, they're all really important, but the closest one to quantum mechanics is the Poisson bracket formulation.
So that extra bit at the end, you say is only
This is if there's explicit time dependence.
if there's explicit time dependence.
In A. So we're assuming that A here didn't have it.
It's not time dependent. Are there situations where you should assume that A is time dependent?
Yeah, certainly, but,
Oh, I guess if A is any observable, I guess.
well, some observables are not gonna be time dependent, like
Right.
the Stern-Gerlach experiment, things are
Right.
time dependent. But there are definitely things where you have, anything that's time dependent, like an oscillating, magnetic field or something like that, then you have some time dependence. You have to take that into account. Okay, all right, so just to make contact here with the book. If you take this equation, which is the operator equation of motion of Heisenberg, and you just take the expectation value at time 0, you get the equation 416 in the book, which is psi 0 d by dt of AH. So we're just surrounding this equation with these psi 0 bracket. So this is I over h bar, and then now we can write psi 0 dagger t a. This would be psi of t, because okay. So this is equation 416. So it just comes from squeezing this on both sides with psi 0 of t. Okay, so now that we've done some work with a Hamiltonian, let's go ahead and actually explicitly introduce one. So this is section 4.3 in the book, and we'll talk about precession. So let's talk about the precession of a spin 1/2 particle in a magnetic field. And so you can think of this as just an electron, and let's let the B field here just be along the z hat direction, okay? So we have, right now, just a static B field, okay? Along the z direction. And we have classically the energy is minus mu dot B. That's just the energy of the spin if it has a magnetic moment mu in the field B. And in quantum mechanics, we'll write this as H. We want to introduce the Hamiltonian operator. And this will be minus mu times B again. But now we have mu, this mu contains the spin, angular momentum. Operator. magnetic moment here, it's gonna contain that operator. And so mu here is actually an operator. Now, if we have if B is only in the Z direction, then this will equal minus mu hat Z times BZ. Okay, but mu hat Z from what we wrote down before at the beginning of the semester here was minus the magnitude of the charge times Q over 2 MC, I think, 2MC. So we have an overall minus sign. We have an overall minus sign out here, and then this was SZ hat BZ.
Wait, so you put two negative signs there? Oh, because the
charge
negative in
of
front of the,
electron is negative.
yeah, I see, because there's a negative in front of the mu, I see. Okay. So, oh, because the negative in front of the mu, that's why we have two.
Yes, yeah. Yeah, this negative is this negative, and this negative goes with the E. Okay, so let's group a bunch of this together. So we'll group together the magnitude of E, Q over 2MC, and BZ, and we'll call this omega 0. It has units of frequency. Oh, sorry. Q is G. I've already got the charge in there. This is G. Okay, so this is this frequency here depends on B0. Okay, this is important for magnetic resonance applications. So we have so our Hamiltonian is really simple then. So H is just equal to omega naught SZ. Okay, so there's no time dependence. It's just a very simple Hamiltonian for if I take an electron and I put it into a magnetic field that has only one component, then we get a really nice simple Hamiltonian. Okay, so now let's apply it to several of our states. So if we take H and apply it to our Z plus state, this is omega 0 SZ hat Z plus, and so this is just plus H bar over 2, so we get H bar omega 0 over 2 Z plus, and then H applied to Z minus will be minus H bar omega 0 over 2 Z minus. So in the magnetic field, if you're pointed up, you have this positive energy, and if you're pointed down, you have that negative energy. So if we looked at an energy diagram here, if this is the Z plus state, and that's the Z minus state, then the delta E here is just, I have to go up to 0, and then this is just h bar omega 0. Okay, so this is the energy diagram. Okay, so if you want to, that means if I have a spin that's pointed down, if I want to kick it into the spin up state, I have to provide this amount of energy to it. And in magnetic resonance, you provide this energy by shining, light, basically, or it's radio frequency for nuclear spins. It's radio frequency. If you use electrons, it's like in the gigahertz range. It's a lot higher frequency. But you can just shine light there, and you can flip the spins up.
So would that mean that, like, if you flip the spin up, it could spontaneously go back to the other spin state if it re-emits its energy?
Yes.
Isn't it like the 21 centimeter line? You learn about that in astrophysics?
That's a hydrogen line.
Oh, right, that's hydrogen spin, not electron.
Right. It's electron energy levels in the hydrogen atom.
Right.
But,
I thought it was because of a change in the spin state of the electron, though, right?
What?
It is because the change in the spin state of that electron, right? That 21 centimeter line? Because doesn't it like to?
I think
it likes to be. It's a lower energy state if it's anti-aligned, and a high energy state if it's aligned, or something like that.
How was it
it's what is it? It's the 2s. Oh, I can't remember the designations for the things. It's 21 centimeters. 21 centimeters. How many EVs is 21 centimeters?
Not a lot.
It might be just a spin thing. I can't remember.
Yeah, I think the energy levels are different if it's like aligned versus anti-aligned. I can't remember which one is higher.
Oh, it's because of the spin of the electron relative to the spin of the proton.
Yeah,
That's
I
what
just
it is.
said.
And when they're it wants to be anti-aligned, like it wants to be spin down, and so having increased energy makes it spin up aligned with the proton.
It's something like that. I can't remember what the if you tell me how many EVs is 21 centimeters, that'll probably it'll make it obvious.
Oh, 5.8 micro EVs.
Yeah. Okay. Yeah. That's like a spin thing. I think the first excited state of hydrogen, it takes, it's on the order of EV. So if it's that small, then it's got to be like a little spin flip or something. Okay. So, but anyway, so let's look at the time translation operator. With this particular Hamiltonian, then we have U hat of t is equal to e to the minus I over h bar. Now, s z hat is this is h, which is omega 0 s z hat times t. But remember that sz hat is the same thing as jz hat, so that u hat of t is equal to e to the minus I over h bar jz hat times omega 0 t. But this is just the rotation operator about the z-axis. This is just rz hat of omega 0 t. So this time evolution operator represents rotation. Around the z-axis. Okay, so this is precession. Okay, so if you just put the spin in the field, if you put a spin 1/2 in a field, it will precess around the z-axis. That's just what it's going to do. So any spin will precess around the z-axis.
Wait, what do you mean by precess around the z-axis? I'm having a hard time visualizing what that
You have an
means.
axis straight up.
Yeah.
Processing is like that. It rotates.
Oh, so that it's the spin is doing that. Okay.
It's like a top, the precession of a
Right.
top in a, like a spinning top in a gravitational field.
Right.
It spins. That's precession.
Right. So the spin itself isn't exactly aligned with the z-axis. It's precessing around it.
Right.
Okay. Makes sense.
Okay, so if we want a precession of 2 pi, or it would take this is just phi, the angle. So we would need omega 0 times the period of that precession, which would be 2 pi. So the period is 2 pi over omega 0, or omega 0 is equal to 2 pi over t. So let's look now, let's do an example. Let the initial state of the spin be in the x plus direction. Or I shouldn't say that, it's just in the state x plus. That's not a direction again. And now let's calculate what the ket will do at later times. So psi of t will be the time evolution operator acting on the ket x plus. And again, this is e to the minus I over h bar omega 0 sz t. And x plus we should now represent, because this is we're using s in the z. We're thinking about this in terms of our z basis operator. So we should convert this x plus to the z basis. So that's 1 over the square root of 2z plus z minus. Okay, and now we have 1 over the square root of 2. Now what happens, I have an exponential and I'm operating, in my exponential I have this operator and it's going to operate on z plus. So what can I replace that sz with here?
Can you say it again?
Well, we have so in the exponent here is this operator sz, and it will be operating on each of these kets. So what can I do if I know that sz has, this is an eigenket of sz?
Isn't it kick back in h bar
What can I
over
do?
2? Isn't it kick back in h bar over 2?
Right, where do I can put that in the exponent, yeah or no?
That's
Yeah, we can, remember?
yeah.
So this will be then e to the minus I over h bar. Now I'll have omega 0 h bar over 2 for this plus z. That's z plus e to the minus I over h bar omega 0, and now we have minus h bar over 2 t times z minus. Okay?
Mm.
Now I can cancel some, let's cancel some of our h bars. Let's just rewrite this so that it's a little bit, this is 1 over the square root of 2 e to the minus I omega 0 t z plus e to the, oops, that's right, plus I omega 0 t z minus. Okay? So this is psi of t. So it started out, at time 0, this was the ket x plus. Okay? Is the ket x plus, is this a stationary state?
Its probability is 1. It's that.
Well, X,
What's the definition of a stationary state?
it does not move.
Not time dependent?
Well, it says there that, it's equal to, cat size 0, right? So there's no t there.
A stationary state is one where I can pull all of the time dependence out to the left and then be left with a ket that has no time dependence. So if you look at this particular ket, I can write psi of t is equal to, I can pull out, let's pull out e to the minus I omega t. Over the square root of 2, and then I'll have z plus e to the 2I omega 0 t z minus. Okay, so no matter what you do, you can't pull out all of the time dependence. I've pulled out some time dependence here, but what's left is still time dependent. So this is not a stationary state ket. Okay. Did I leave off a factor of 2?
Yeah, it's over 2.
Oh, yeah, these are all 2. 2, 2, this is a 2, and this is a 1. Okay, yeah.
So basically, you gave us an initial state, and we did the operator on it, and did some figuring, and at the end we said, oh, we can't pull the time all the way out, so we now know it's not time independent, and so I guess.
It's not, well, it's not a stationary state.
Oh, it's stationary state. Oh, right, okay, stationary state. Oh, I thought it said capital Q at later. Okay.
Okay, so let's look at this ket then and ask a couple of questions. So, what's the probability that the measurement would find z plus or z minus for the state?
So I'm assuming you would operate on it with the C plus, and you would pull out the Z.
So what are the probabilities?
Oh.
If you square the probabilities,
Well,
you
you're,
just-
oh, it's zero, well, you, they would, you would do the negative, you would do the complex conjugates, and you would get zero because they'd add, and the things would add, one's negative, one's positive, you added, oh, it's one, because they added yeah, because they added zero, so e the zero is one. Does that make sense?
Yeah.
Okay,
The exponents are gonna add
right.
to zero, which will give you one, but you still got the factor of.
Oh, one over square root two,
One
good,
over
because they
square root
can't
two.
both be one, because the probability is doing that, right?
Well,
So,
it's a half, right, for
Half.
both?
okay.
Either state.
Which is what you want, because you want to add to one when you add. Okay.
Everybody see that? If I take, say, z plus with psi of t, that gives me 1 over root 2 e to the minus I omega 0 t over 2. Right, that's the amplitude. So when I take the complex conjugate of this thing, I'll get a plus here, so when I multiply them, these things will just go to 1. Everybody got that? Okay. So what is the probability that a measurement will find x plus, what about x plus?
You can rewrite your z's to x's
You gotta convert to
and substitute it,
x's.
or you do the other way where you apply both, and then, I don't know which is easier.
Well, let's do x plus.
Okay.
I'll have e to the minus I omega 0 t over 2 divided by root 2, and then in here I'll have x plus with z plus e to the plus I omega 0 t x plus with z minus. Right, and so now we have to just calculate what are these amplitudes, x plus with z plus and x plus with z minus.
Okay, so z would be 1 over square, it's like you would look at what the z, you'd expand it out to in x terms, and then you would just take the x plus part of that. Is that not making, I'm not explaining it?
Sure, we can also just do it,
Oh,
this is, x is 1 over the square root of 2 of 1, 1, z plus is just 1, 0, right? So this amplitude is just 1 over root 2. And then x plus with z minus is also just 1 over root 2. Does that make sense? Okay, so we have an overall factor of a half then. So we have a half, and then I can just redistribute this exponential again. This is just e to the minus I omega 0 t over 2 plus e to the plus I omega 0 t over 2. Does anybody recognize that function?
it looks like, oh, I was gonna say it looks like a sine and a cosine, there's an I there.
Oh, okay.
It's a cosine, right? So we have the x plus psi of t then is equal to cosine omega 0 t over 2. So the probability of getting x plus will be cosine squared omega 0 t over 2. Okay, so if you work out then x minus, p of x minus, it's just the sine squared of omega 0 t over 2. So they add to 1 like they should. Okay, and if we calculate the same things for y, well, let's just go ahead and calculate it. Let's calculate y plus psi of t. So we need, this will be equal to 1 over root 2, and we'll have e to the minus I omega 0 t over 2, y plus z plus e to the plus I omega 0 t over 2, y minus z plus. So this amplitude is, it's 1 over root 2, so y plus is 1 I, so this is 1 minus I, because I have to conjugate when I flip it, times 1 0, so this is equal to 1 over root 2. And then this amplitude is a y minus, and that will be 1 over root 2, 1 plus I, 0, 1, and this will be I over root 2. Is that right? So y plus psi of t will be a factor of a half, e to the minus I omega 0 t over 2, plus I e to the plus I omega 0 t over 2. All right, did I make any mistakes there? I don't know. This doesn't look right.
Yeah, it looks the same as the X.
No, I've got an I here.
Yeah, I see it, sorry.
So if we take the, let's see what we get if we calculate the magnitude squared, then we'll have a quarter, and then, let's see, I'll have e to the minus I stuff plus I e to the plus times e to the plus I stuff minus I e to the minus stuff. So this will be, that's 1. minus I e to the minus two I stuff plus I e to the plus two I stuff. And then this will be plus, and then this will be 1. Okay, so this is a quarter, 2 minus, sorry, 2 plus I times cosine of 2 over 0 t. Wait, twice, there's 2 in here. So this is 1/2, 1 plus I cosine 2 omega 0 t over t. Okay, wait, there's a mistake in here. Anybody know why there's a mistake in here? How do you know for sure there's a mistake?
Is it that you're not supposed to have an eye left hanging out?
That's right.
Yeah.
Yeah, it can't be
'Cause
imaginary.
it's supposed to be a real number, right?
Yeah, it has to be a real number, so where do
Is-
they?
Is E plus,
Wait a second, what did I do wrong here? Oh, wait, I, no, that's right.
When you multiply the complex conjugates, it's supposed to, no, it's supposed to.
Oh, but it's not a complex conjugate at the top, because, you're doing e to the negative I. Wait. Oh, it's because yeah, you're doing e to the negative I plus I, e to the plus I, which the part next to it's not the conjugate, right?
I don't see any errors right now, but it's definitely wrong. Let's see, oh, I'm just doing something wrong here.
I'll go ahead and send your recommend you for a Nobel Prize. You've broken quantum mechanics.
Yeah, I don't think so. Okay, I just made some stupid mistake. So, let's see, where is it? Did I do something wrong over here? Because I know that we have to get, let's see here. That's right.
I don't wanna interrupt your process.
Oh, did you find it here?
So we'll skip it up here. This isn't the conjugate of this, I don't think, because this is a different, like, if it's like, you know, A plus BI, this is a different B, these two aren't equal to each other, right?
Well, you have to just, you just conjugate the i's.
Okay. Oh, you conjugate all I's, okay.
So I just conjugated all the i's.
Okay. Then I'm wrong about being wrong. Wrong about it.
Okay, well, all right, this is wrong. So, what time do we have? I don't wanna take up the whole,
It's 4:31.
it's 4:30?
Yeah.
Okay. Let's leave that there, and I wanna come back to it later. but let me calculate one more thing. So we'll finish that here after, if we run out of time. Okay, let's see, did I calculate? Let's calculate, the expectation value of Sx hat in this particular wave function. So what we want is, psi of t, Sx hat, psi of t. And we know psi of t, this is it right here. So and we also know Sx in the z basis, this is just 0, 1, 1, 0 with a factor of h bar over 2. Okay, so then z itself is just, psi of t is this is 1 over the square root of 2. And let's write it in the z basis. This will be e to the minus I omega 0 t over 2. And then e to the plus I omega 0 t over 2. And then the bra will be the vector here, 1 over the square root of 2. And then we'll have e to the plus omega 0 t over 2 and e to the minus I omega 0 t over 2. Okay, so if we do this matrix multiplication, let's get rid of we've got a factor of 2 from these and then a factor of 2 from here, so we'll have h bar over 4, and then we'll have e to the plus, e to the minus, 0, 1, 1, 0, e to the minus, e to the plus. So that's h bar over 4. Plus, minus, and then this will be e plus, e minus. So this is h bar over 4, e to the 2 plus, plus e to the plus 2 e to the minus 2. Okay, so we have the Sx hat in this wave function is h bar squared over 4, and then we have the stuff that I was mentioning is this is e to the twice the stuff, so it's I've got a plus I omega 0 t and then plus e to the minus I omega 0 t. So this is that's h bar over 2, and then I can bring a factor of 2 in here, and this is cosine omega 0 t. So the expectation value is h bar over 2 cosine omega 0 t. And then let's calculate the expectation value of xy hat. So knowing that representation, so we'll do the same thing here. We'll have h bar over 4, e plus, e minus, and then s is 0 minus I 0. I believe that's right? All right, so you guys are supposed to be checking me here. Is that?
I'm sorry, I'm preoccupied with that over there. I can't help it.
This is SZ, right? I think it is. I think the minus side is okay. So this gives us H bar
Yeah, that's right, that's
over 4. And now we'll have E plus, E minus, and this will be minus I, E plus, and then I, E minus. So this is H bar over 4 I, and now we'll have e to the minus 2 omega 0 t, or sorry, minus omega 0 t, minus e to the plus I omega 0 t. Okay. Yeah, that's right. So this is minus I H bar over 2 times the sine of omega 0 t. Is that right? Yeah, okay, that's gotta be right, because, okay, so this is SY. Now we should be able to check, you see this is SX. Use our operator equation of motion and check it. Okay, so if we had d by dt of Sx hat in this state psi, this has to be equal to I over h bar times the expectation value of the commutator of h with Sx. Okay? So h is just omega 0 sz hat, so the commutator of h with Sx hat will be omega 0 times the commutator of sz hat with Sx hat. And that will be sz Sx is IH bar Sy hat. So the right-hand side of this is I over h bar times omega 0 IH bar expectation value of Sy hat. Okay? So this is canceling my h bars. This is minus omega 0 expectation value of Sy. D by dt of Sx, it should be that. And so we have d by dt of this is, d by dt here will just be omega 0 h bar over 2 times the sine of omega 0 t. And let's see, so all right, so we found Sy hat. I can cancel my omegas from either side, is minus h bar over 2 sine omega 0 t. Okay. I have an I here in the. All right, so are there any questions? Has anybody figured this out yet?
I got a question about it.
Yeah.
So those vectors you wrote for y plus and y minus,
Yeah, are they wrong?
that's what I'm asking, because it's the only thing I can think of that would make that wrong, is that those vectors might be wrong.
Well, look in your notes. What did we write down for y plus? I thought, oh, it is wrong, it is wrong.
You have them swapped.
It is wrong. Yeah, those are wrong. Okay, that's why.
Which part's wrong?
Wait, I'm not sure. That's right.
So with the y negative and the bra and the z plus head, isn't that like measuring y plus and y minus after running a beam of electrons through a Stirring Gerlach and SGZ? So the probability of it being a y plus.
Well, we know that,
50%.
we know that y plus minus, z plus minus, the magnitude squared has to be a half.
Right.
But the
Well, we
amplitude
have
itself, you can have, is this what we wrote down for i's before? For y
Yeah,
plus?
that,
Yeah.
that, yeah, so
Yeah,
you have
that's
them
right.
swapped. You put that first one,
Yeah,
Um,
you made a sign error.
No, because this is y, that's the
Yeah.
cut y.
Yeah,
well,
that's the
but I'm
cat.
saying for
Oh, I
y
see.
plus, oh.
So
No,
y,
yeah, that's-
y plus bra is equal to 1 over root 2 1 minus I.
Yeah, I checked that in the beginning, and I that was the first thing I looked at, and those are right.
But if you square I over square root of 2, that's negative.
But the magnitude squared will
Oh,
be a half.
I got you.
Okay, wait, then it's this then. Well, let's just, okay, I mean, well, there's only one way to figure it out here. I mean, if I have e to the IA plus IE to the IB, what's this? This is equal to cosine A plus I sine A plus I times cosine B plus I sine B. So this is cosine A plus I sine A plus I cosine B minus sine B. So this is cosine A minus sine B plus I sine A plus cosine B. I don't know if it's, okay, maybe that's the mistake in there. Why don't I just write, let's see here, I is equal to e to the I pi over 2, right? Is that right? Is I e to the I pi over 2?
I think so.
So let me just write that as. Oh, let's see here. So this is equal to a half. Let's call this stuff alpha. This is minus I alpha, so let alpha equal to plus e to the I alpha, plus pi over two. Right?
What about, are you carrying that I down?
I'm using this.
Oh, okay.
So that would be a quarter, and then I'll have, I'll have the e to the minus I alpha, I'll have a plus one from that, and then I'll get a plus one from this and its conjugate.
Mm.
And then I'll have a plus e to, when I multiply, I'll multiply this times a minus, I'll have e to the minus two I alpha minus I pi over two. Plus e to the plus two I alpha. Well, this is. So that's a plus, and this is a minus pi over two, right? So that's a quarter, two plus, and this is, two times the cosine of two alpha. Okay, let me write this out. So multiply these guys, I will get e to the minus two I alpha minus I pi over two, and then here I will get, okay, plus e to the plus two I alpha plus I pi over two. Yeah, okay, so this is equal to, yeah, so the answer is real. So what is this? One plus cosine of, let's see, sorry, no I in the cosine here. It's just two alpha, that's omega zero t plus pi over two. Okay. Okay.
Would that be a sign if it's plus a pi over two?
Yeah, is it plus sign? I can't remember.
Because cosine's like this. So if you add pi over two, it shifts it backwards with that negative sign. Let's see, if I have a cosine and I add pi over two, it's the sign, it's just sign, right?
Yeah.
So this is 1/2, 1 plus sine omega zero t. So, is that right? this should be the amplitude squared. So,
At least it has a,
That's
it has,
right,
it has a
okay.
chance of being right, 'cause there's no ice.
well, I mean, it's right because the probability can't be any larger than one, and when it's reached its maximum value, the sign will be one. So I'll get a one, and then sign will go to -1, so this probability will
Hmm.
just, flop.
Uh,
through zero.